Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Hey everyone, before we get into today's episode, we are going to start doing short bonus episodes on the off weeks where we're going to answer your questions. We've had lots of interesting questions from you all that have come up based on things we said in previous episodes, and we really want to answer those. So send us your thoughts on social media. We are at Planet Geocast, and our email is planetgeocast@gmail.com, and we'll provide some answers. So tune in next week for a short answer from one of you listeners. All right, let's get into it. All right, let's do some introductions. Chris, you are Chris Bullheis, high school science teacher extraordinaire in the great state of Michigan. I am Jesse Remick, geoscience professor at Penn State and your former student. And this is Planet Geo, a podcast where we talk about some amazing aspects of our planet and why they matter. All right, how you doing today, man?
I'm doing great. How are you doing, Jesse?
I'm doing really well. So today we have the greenhouse effect. Man, this could be a fun episode.
Yeah.
We're going places today.
I know. This is a punchy topic, it's a hot topic, but let's go.
Totally cool. All right, hit me. What's the summary? Where are we going?
Yeah, so we're going to start off with the history of the greenhouse effect, which is quite old and actually awesome and fascinating. Then we're going to go into how the greenhouse effect works, and then we're going to talk about why it matters, and then finally we're going to talk about how CO2 is regulated by rocks in the oceans.
Hey man, that's our jam right there, man.
I know. It's hard rock stuff, right?
Rocks control CO2. What a beautiful thing.
Right on. And then we're going to end up with talking about an analogy with Venus, the runaway greenhouse effect on a nearby planet.
Oh, so cool. I love Venus. I'm so interested in Venus.
I know.
Super cool.
Venus is out and about, almost every night here. It's so cool to see. Yeah. So
totally cool.
Well, hey, let's go.
Yeah, so I mean, this is a hot button topic, right? The greenhouse effect, or at least climate change, is a hot button topic. And so we want to get a couple things out in the open right now, right before we start going into this. And one of them is that we're going to be talking about the greenhouse effect, really like the basic science behind how the greenhouse effect works. And it's something we've known for a long time, right?
Yeah, this episode, Jesse, we're going to try to stay away from opinion, no politics, no hyperbole. Some of you might be saying, well, here's a couple hard rock guys sitting around talking about climate science and
hard rock. That's not our music choices. It's the types of rocks we like. We like gneisses, we like granites. Actual hard rocks.
That's what I meant.
Yeah.
So, but I'm an earth science teacher. I'm a geoscience teacher, and I teach astronomy in high school. My career goes back 25 years, and during the course of my career, I've had to fight to keep earth science and geoscience in the high school.
Oh, is that right?
We're always struggling for legitimacy here. And the next gen science standards that have come out now, earth science has been elevated to, it's always in the media. It's always there. We're hearing about these things all the time. And so the next gen science standards reflect that.
Okay, that's good. So you're feeling a little bit more comfortable that earth science is being taken seriously at the high school level for educationally.
Right. And because it's taken seriously, then I take it seriously in terms of, the way I teach it.
Well, listen, you've always taken it seriously. You don't mess around. But okay, well, no, that's interesting. I mean, from my perspective, I don't study climate change. I study ancient rocks and how, weather plate tectonics operated 4 billion years ago, all this kind of stuff. But I'm at Penn State now, and Penn State has a lot of quite famous climate scientists, and it's just part of the conversation. Our department at Penn State also has a lot of oil and gas connections, right? And a huge industrial link, which is extremely important for our university, our department, and, the economy of Pennsylvania. So it's a really, interesting cross-section. It's just always in the conversation of all geoscience discussions because it's important, right?
Right. It is extremely important, I think.
That's right. So
I know.
So, okay, it's very, hot button right now, but there's a long history of understanding the greenhouse effect. Isn't that right, Chris?
Yeah, it's been around for a long time. Actually, it goes back to the 1800s when scientists measured the heat trapping ability of certain gases. And one of those gases was carbon dioxide. And that's amazing. I mean, that's a long time ago. We didn't know a lot back then, but we knew this.
Oh, yeah. That's impressive that we were understanding the greenhouse effect that long ago. Very cool.
It is.
Very cool.
And so let's jump into a couple examples of that. In the 1820s, Joseph Fourier, who was a mathematician and physics guy and so on, he looked at our climate balance, the incoming solar radiation, the outgoing solar radiation, and so on, and he figured that our climate should be much colder than it is. And so he started to wonder about why that is.
Yeah.
And he figured it out, that gases are trapping radiation. They're trapping heat. That led to then his discovery that our atmosphere acted like a greenhouse. And that's really when the phrase was coined, the greenhouse effect.
The greenhouse effect is a very self-explanatory term. I mean, it's walking into a greenhouse in the wintertime. There's greenhouses all over Michigan, right? To get the starter plants going in the springtime because it's freaking cold. But
it's amazing, yeah.
But it works. Yeah. The greenhouse effect works. You walk in the wintertime and it's warm inside, nice and steamy, little plants are growing. The greenhouse, it works. And it also works on a planetary scale. Although the analogy is not a perfect one. The greenhouse effect on a planetary scale does not work in the same way as a greenhouse does. But it's close, and we'll get into that here.
Right. And then, so back in the 1860s then, so 40-ish years after Fourier, John Tyndall, actually, he measured the ability of carbon dioxide to trap infrared radiation.
Oh, interesting.
So he was able to quantify this in terms of its ability to trap this radiation emitted by the surface of the Earth and trapped by carbon dioxide. And that's absolutely amazing. So this is not new stuff. This goes back to the 1860s. We didn't know a lot back then.
No, definitely. I mean, this is before our understanding of the atom and, before we understood nuclear physics and all this stuff. It's very cool.
It is. But here's the thing, is that this knowledge predates any discussion about greenhouse effect and climate change at all. And this is now, since, of course, our ability to measure this has been enhanced greatly. So the 1860s is where it started and they measured this. But now we know exactly carbon dioxide's ability to trap heat and other greenhouse gases too. It's not just CO2, it's other gases also.
Yeah, we know it very precisely.
I want to point out that it wasn't until 100 years ago that humans finally entered the scene in terms of maybe impacting our climate. These chemists and physicists, they didn't think of that at all. We were not manipulating our atmosphere at all. They just did the science on it, right?
Right. No, it's a very interesting story of, the story of energy is an extremely interesting one. I mean, people were burning wood and coal a long time ago, but the first oil well was actually drilled in Pennsylvania, and it was drilled, I think it was like in the late 1800s, but it didn't catch hold on a large scale until in the interwar years.
Well, and it certainly never dawned on these chemists that maybe humans are having an impact. No, this was just something that Earth is warmer than what it ought to be. What explained that? And they proved it right there. What explained it is that we have certain gases in our atmosphere that trap heat. And you know what, Jesse? It's a damn good thing that happens. Because if you like living on this planet, then you're a fan of the greenhouse effect, right?
Oh, yeah, totally. It's what makes Earth habitable. Absolutely. And it's what makes Venus uninhabitable, and it's what makes Mars uninhabitable. So we'll get to that. But
so, all right.
What's actually going on? I mean, how does this work? What are we talking about here?
So I think it's important when you think about the greenhouse effect and how this works is that you have to follow radiation from the sun.
And radiation is energy. This is energy with different wavelengths. Light is part of this whole spectrum.
Visible light, yep.
Visible light is part of this whole spectrum. Microwaves are part of this whole spectrum. It's energy that travels in a wave. That's what we're talking about in radiation here.
And when we talk about the greenhouse effect, we need to follow the radiation from the sun, but only a little bit of it. We don't need to follow the entire spectrum. We don't need to follow the X-rays and the gamma rays and the UV rays and any of that. What we're following is visible light and infrared. The sun emits all of these radiations that you talked about and I talked about. In terms of keeping our planet warm, we're concerned about visible light and infrared. That's it. Right. So we need to follow it coming from the sun. It's radiated. It comes in. Now, when that radiation hits the surface of the Earth, some of it is reflected and some of it is absorbed.
The stuff that hits glaciers is typically reflected, and the stuff that hits land and oceans and stuff like that is absorbed more, or at least a higher proportion of it is absorbed.
Now, what reaches the surface, though, is important to acknowledge. Not all the radiation reaches the surface. Most of the infrared doesn't reach the surface because it's absorbed by molecules in the air. Most UV doesn't either because it's absorbed by ozone. But what does reach the surface of the earth is visible light, which is what we see. Okay. So this light reaches the surface. About half of it is absorbed. Now that absorbed radiation is then going to be re-radiated. And I think that's an important point to emphasize, that it was radiated once from the sun. Now it's re-radiated back by the earth, but it's different. It's now longer wavelength. It's not the same wavelength that it came in.
So let's go back to re-radiating, because this is kind of a hard concept to understand. When you get radiation, these are like energy waves coming in. Molecules absorb this energy, kind of makes them vibrate faster a little bit. It sometimes bumps electrons around, and then everything kind of calms down. And during that atomic calm down, it's re-radiating energy. It's kind of losing that energy back out, and it's changing fundamentally the wavelength and frequency of that energy that's being re-radiated. So it absorbs it, and then it kicks it out as something different. And that's a hard concept to understand, but
I think you said it very well. Here's an analogy, right? If you stand at on the 20-yard line of a football field, and I'm at the goal line, and I take a running shot at you, just to
okay. I mean, first of all, I'm going to lay your ass out. So let's get that clear right away.
Oh, that's funny, because you seem to be forgetting, Jesse, that when we were on Summer Science playing water football, I absolutely destroyed you. I ran you over.
Oh, man, you did. I forgot about that. Oh, man, I was so cocky, man. And that's right. We were playing water football. We were like in knee-deep water. And I thought, oh, it's my teacher. He's going to take it easy here, And no, you just like full-on truck stick over me. Oh, man, I forgot about that. All right. So you're on the 20-yard line.
All right, we digress.
I'm powering in the end zone.
Yeah, here's the way this goes, though, is that, when I transfer my energy to you, I send you in motion, but I also lost some of my energy, right? Yeah. And so that's what happens when visible light hits the surface of the earth. It sets those electrons in motion. So some of the energy that it had coming in is lost. And so it's re-radiated at a lower energy.
Right.
Does that make sense, Jesse?
Yep. Exactly.
So it's re-radiated as a lower energy, which happens to be infrared, which is a longer wavelength, and it's heat. So the earth takes this visible light in, re-radiates it as a longer wavelength, infrared. But here's the thing, and why this is so important, is that infrared is absorbed by certain molecules that exist in our atmosphere, particularly carbon dioxide.
Right. So this is important when you're talking about incoming radiation too, because the sun is emitting IR, or infrared radiation, but a lot of that is absorbed by the CO2 in the atmosphere as it's come on its way in. So it doesn't reach the surface. What we're talking about is stuff that is filtered out on the way in, hits the surface, is changed into something else, and re-radiated back out into the atmosphere. It's re-radiated in all directions, really. Part of it goes back up into the atmosphere. It hits these molecules, again, this kind of filter, and it gets absorbed there, which then it gets re-radiated again from those molecules. And some of that goes downward again.
So it's invisible to the molecules on the way in at a shorter wavelength, but it's not invisible to them when it gets re-radiated at a different wavelength. It's now absorbed. And then here's the thing, Jesse, is those molecules, like carbon dioxide, will re-radiate that energy in a totally random direction. Okay.
Right.
And I say that in a very specific way. Radiated once from the sun, re-radiated by the earth, re-radiated by those molecules that absorbed it in the atmosphere. Right. And so the net effect of this all is, Jesse, and I'm trying to paint a picture, and I would draw this on the board if this weren't a podcast, is that we let the heat in and we don't let all of it back out. And that's the mechanism for it.
So we're talking about energy ultimately, and energy and heat, and it's coming in, it's getting through the filter on the way in, hits the surface of the earth, it gets absorbed, gets bounced back, gets radiated that second time, and then it gets trapped. It kind of bounces around between atmosphere and surface a whole bunch. It's ultimately just trapped within the atmosphere because it passes the filter on the way in, doesn't pass the filter on the way out. So it's stuck there.
Right. And some of it is re-radiated back into space. Okay.
Yeah.
And, so it doesn't trap it all. It just traps some of it. And so this is exactly the way a greenhouse works. It's the same mechanism, Jesse, is that, visible light and short wavelength infrared, very short wavelength infrared, can pass through the glass of a greenhouse or the glass of your car window.
Yeah, that's right. I mean, everybody, if you've never been inside a greenhouse, you've almost certainly been inside of a hot car on a sunny day, right? So, and this is the same exact thing, right? So
is.
it's the same
The
exact
mechanism
analogy.
is the same. Visible light and short wavelength infrared passes right through your window. It's transparent to it. It's not there. It's invisible to it. But that radiation gets absorbed by your seat, by your dashboard, by your steering wheel, and re-radiated as a longer wavelength infrared. But that longer wavelength infrared cannot pass through the glass, just like it can't pass through the carbon dioxide molecules.
Exactly.
The difference, though, is with your car, with the windows up, you don't have the free flow of air. So it's a closed system versus an open system and so on.
So that's the greenhouse effect. And there's several, different types of gases that behave like greenhouse gases. I mean, much of our atmosphere behaves in some way like a greenhouse gas.
You're right. There are other greenhouse gases, water, methane, both of which are very powerful absorbers of radiation, more powerful than CO2 by a lot, actually. And water is one of the most potent greenhouse gases that there is. It's the most potent greenhouse gas. So there are many other greenhouse gases. So why are we talking about just carbon dioxide? And that's what you originally led into, is carbon dioxide is the one that we disturb, the one that humans are impacting. So we need to talk about the burning of fossil fuels, right? We need to talk about like a little bit about the chemistry of the burning of fossil fuels, right, Jesse?
All right, yeah. So there's several different things that we burn that produce CO2 to produce energy. And the first is coal. Coal is just pretty much basically carbon. And this is used in a significant fraction of at least the United States power generation capacity. I think it's somewhere around the 20-25% range. And when this is burned, it's basically just combining carbon and oxygen, and that produces CO2. So any of these coal-fired power generation plants are producing CO2 by combining carbon and oxygen together.
So if you burned a pound of coal, 1 pound,
Yep.
how much carbon dioxide would come out?
Yeah, so if you
burning
burn,
that pound of coal?
basically if you burn 1 pound of coal, you're getting about 2.7 pounds of carbon dioxide out of that. And that's just because you're adding O2, two oxygen molecules, to that one carbon molecule.
That's absolutely amazing. When I talk about this with my students, they're troubled by that. Like, wait a minute, you burn a pound of coal. How do you produce more than what you burn? Like, you're saying that if you filled a balloon up with the emissions from burning a pound of coal, that balloon full of gas would weigh 2.7 pounds. That's amazing.
Yeah, it's pretty heavy balloon. Yeah, no, we're actually creating, because we're talking about carbon and we're talking about carbon dioxide, carbon 2 oxides. So, we're adding oxygen to this thing. And so when we talk about carbon emissions, we're often talking in units of mass. So we're talking about tons of CO2 and all all this stuff. So yeah,
and people don't often think about that, do they? They don't
No,
think
that's
about
right.
that gas has mass, which it certainly does.
And it's not an easy thing. But there are other hydrocarbons, or there are other power sources that produce CO2, right?
Yeah. So let's just real quick, we'll cover two, right? Two other ones other than coal. We'll cover methane because that's what most people heat their homes with.
Okay.
Methane is called natural gas, and natural gas is made up of 1 carbon atom and 4 hydrogen atoms. So now we're into the hydrocarbons, molecules that are made up of hydrogen and carbon. When you burn a hydrocarbon, then it combines with oxygen to create carbon dioxide, just like coal did, and water. So those are the main emissions that come off from burning methane or natural gas. CH4 plus O2 yields CO2 and H2O. This is what I'm heating my home with right now tonight. And then the other major hydrocarbon that we're going to touch on is gasoline. And gasoline is mostly, it's complicated, okay, but it's mostly octane. And octane is C8H18. And when you burn that, you have to have oxygen. So it combines with oxygen to produce, again, carbon dioxide and water.
Yeah.
So there's a common
if you burn, let's go through the same example we did with coal. If you burn 1 gallon of gasoline, which is about 6.3 pounds or so, how much CO2 do you get?
That produces about 20 pounds of carbon dioxide coming out of your tailpipe.
Okay.
But interesting, Jesse, when you pull up to somebody at a red light, and you're sitting behind them and you see water dripping out of the tailpipe, it's because water's dripping out of the tailpipe.
Yeah, it's producing water too.
That's the other byproduct of burning the gasoline is water.
That's right.
And when you put water in the atmosphere, it lasts a day, a week, but not much longer. So it's not a valid comparison because of the hydrologic cycle being completely different from the carbon cycle, which I think is a great segue into the carbon cycle.
Yeah, no, totally. You're totally right, Chris. I mean, so there's cycles on Earth, right? Carbon is moving through different reservoirs on Earth at different rates. And this is kind of where in our wheelhouse, right? And this is super interesting stuff because it involves rocks. It's ultimately controlled by rocks in the ocean.
Yeah.
So let's get into it.
When we talk about the carbon cycle, we talk about different spheres that we have on Earth. And these aren't like literal spheres like you think of the sphere of the Earth or something like that. These are just general areas. So we talk about
these are like
one of the
categories of stuff on Earth. These are just like categories of things.
Yeah, like the geosphere is all things like rock and surface of the Earth related and interior of the Earth related, right? That's the geosphere, Earth related. Then you have the hydrosphere, and hydro means water. So that's all things water related. You have the atmosphere, which is all things air related and that envelope that encompasses the geosphere. And then you have the biosphere, which is all things life related.
Right.
And so those are the four spheres that drive the carbon cycle.
It's super cool stuff. But for our purposes, we're going to talk about two different cycles, a slow carbon cycle and a fast carbon cycle, right? And the slow carbon cycle is really governed by rocks in the ocean, in volcanoes. The fast carbon cycle is much more governed by life and, plants dying, plants and animals living and dying and breathing, okay? But the slow carbon cycle, let's get into that because it's really plate tectonics. And so see episode 2 to hear more about plate tectonics.
It is. I mean, we're talking about things like, carbon being emitted out of volcanic eruptions and things like this.
Yeah, I mean, loads of CO2 comes out of volcanic eruptions. So this is the slow carbon cycle that we're talking about, right? So let's break this down. Let's go through this in detail. There are a couple steps to this slow carbon cycle that kind of regulates CO2 concentrations in the atmosphere, right? So what we're going to do to illustrate this slow carbon cycle is we're going to take a single carbon atom and we're going to trace it through the carbon cycle, this slow carbon cycle. So we're going to start with a carbon atom in a CO2 molecule in the atmosphere. It's a gas, it's in the atmosphere. It's doing this greenhouse effect, right? It's absorbing radiation, long wavelength radiation, it's re-radiating it, That CO2 molecule will perhaps end up being absorbed in water.
So when that carbon dioxide gets absorbed into the water, what does it become?
It becomes carbonic acid. This is an acid that helps dissolve rocks, really. This is what makes hard water. This is what's making the ocean salty. So now it's in water. It's dissolved in water, and it is carbonic acid. And then what does it do, Chris?
Yeah, so that carbonic acid dissolves rocks. And one of the main rocks that it dissolves is limestone. And
your favorite rock to eat.
I do like to eat. Well, come on now. All right. But I do like to eat limestone. It works.
It works.
Not for nourishment, unfortunately, because if I could eat rocks for nourishment, I would. But I can't. So anyway, yeah. It dissolves limestone and it carries that to the oceans. And when the oceans get saturated with limestone, they start to lay down limestone. And so that calcium carbonate, there's carbon in the carbonate.
That's right.
And
so that carbon,
that's that atom. It came out, it was a carbon dioxide molecule, got dissolved into water. It formed carbonic acid. It dissolved rocks, which carried that carbon atom now to the oceans. And it gets precipitated as a rock now that is called calcium carbonate, which is the same as calcite or limestone. And so that carbon atom now is at the bottom of the ocean. So what happens to that then?
Yeah, that carbon atom is now sitting in a limestone at the bottom of the ocean. And because it's that oceanic plate is going to subduct in a subduction zone due to plate tectonics on Earth, it's going to ultimately come out as a volcanic gas probably. So that limestone gets subducted, it gets heated up, it gets melted. Now that carbon atom that's in calcium carbonate in the rock, it's going to end up in a magma, which ultimately is going to erupt and come out of a volcano as CO2, the gas. So now that carbon atom is now back in the atmosphere. We have completed this slow carbon cycle.
Yeah, it's awesome. I mean, and it is the slow carbon cycle. I mean, those processes that you just described take millions of years to happen.
That's right. And they take millions of years, and they're extremely important for regulating our climate on a long-term cycle on this millions of years timescale. Because what this tells us is CO2 is a greenhouse gas. We know that. So more CO2 in the atmosphere, more greenhouse effect going on. But what we've talked about in this slow carbon cycle is that we're taking CO2 from the atmosphere, and because it's weathering, because it's going through carbonic acid, it is actually ending up in rock at the bottom of the ocean. So the ocean is taking CO2 out of the atmosphere and pulling it down and putting it into rocks at the bottom of the ocean basin. So it's very important for long-term regulation of climate and keeping CO2 out of the atmosphere and in a rock phase.
So it went from the atmosphere to the hydrosphere to the geosphere back into the atmosphere. That's how they all interact.
Yeah, so there's a couple interesting things in this, but first of all, that's the slow carbon cycle. And then there's a fast carbon cycle too.
The fast carbon cycle, one of the main processes that have an impact on the fast carbon cycle is photosynthesis. And this is absolutely fascinating. The amount of carbon dioxide that is removed through the growth of plants on this earth is amazing. And we can measure, actually, on a year-to-year basis, the ups and downs when plants are growing in the northern hemisphere and then when they go dormant. We can measure, actually, the CO2 levels drop during the spring and summer, and they bottom out in the fall. And then CO2 levels rise all the way to the end of winter when spring starts again, because there's very little organic material taking carbon dioxide out of the atmosphere. It's an amazing cycle, and it's very important. And that's the fast carbon cycle.
It's totally important. Because most of the continents are in the northern hemisphere, during the northern hemisphere summer, this is when all like the leaf growth happens, and it pulls a lot of CO2 out of the atmosphere. But for the importance of the greenhouse effect, we're talking about yearly averages. So this stuff kind of averages out. But anyway, that's the fast carbon cycle. I mean, photosynthesis has a major effect on the seasonal fast carbon cycle.
The carbon cycle, what we forgot to mention is that the slow carbon cycle involves the formation of the rocks like coal and the rocks that we get our natural gas from and petroleum from.
That's right. So we have plant life and biology ending up as rocks. So part of what we just explained as the fast carbon cycle ends up as a rock in the slow carbon cycle as hydrocarbons buried in the rock record. And so humans, when we burn hydrocarbons, we're taking carbon from the slow carbon cycle and kind of putting it in the atmosphere in this sort of fast carbon cycle. We're linking both of these cycles together in a way that disturbs the system a little bit.
A little bit, yeah. A lot of it. I mean,
it's totally right. Totally right. Yeah. So let's put some time frames on these different cycles, right? The fast carbon cycle we're talking about, this is operating on the years, seasonal kind of basis. The slow carbon cycle, this carbon, being buried in rocks, coming up through volcanoes, this operates on hundreds of thousands of years, right? For this system to balance out, it takes hundreds of thousands of years.
All right, Jesse, then let's transition then into, is there an analogy nearby, a planet nearby that shows us what can happen when you get a runaway greenhouse effect?
Oh, yeah, totally. I mean, so this is something that's really interesting to me personally in my research field is Venus. Venus is closer to the sun than us. It's about the same size. It's chemically very similar to us. I mean, the bulk planet is chemically very similar to Earth, but it's extremely different. I mean, it's uninhabitable, it has a super thick atmosphere, right? But there's a lot of ideas out there that suggest that Venus and Earth in their younger years back in the day were actually quite similar, that Venus probably had an ocean at some point in time. It no longer does, though. And Venus is the ultimate greenhouse planet, right? I mean, what are the surface temperatures on Venus right now?
Right. I mean, Venus is in excess of 450 degrees Celsius, and that's day and
so
night.
Hot. Yeah.
I mean, how hot does your oven get at home, right? I mean, this is almost twice as hot as that.
Yeah.
It's really hot. But the thing is, Jesse, is that a day on Venus lasts over 120 Earth days. Imagine a night that lasted over 120 days, which is 4 months. How cold would it get? But Venus, the temperature doesn't change much because the planet is this runaway greenhouse. And the air pressure on the surface is 93 times greater than what it is on Earth. But you know what it's made of, Jesse? It's made up of 95% carbon dioxide.
So there's loads of greenhouse effect going on Venus, which is why it's so hot on the surface. But the really interesting thing about Venus is the reason for why all that CO2 is in the atmosphere. And this has to do with a lack of a slow carbon cycle on Venus.
That's right.
So Venus used to have oceans. Almost certainly, like in its early days, 3 billion years ago, Venus probably had some ocean there, which means that, again, we come back to Earth in the slow carbon cycle. When you have an ocean, it means you can take CO2 from the atmosphere, dissolves in water, dissolves rocks, ends up as a rock in the sea floor. That was going on in the early days of Venus. When the oceans dried up, all of a sudden you can't pull CO2 out of the atmosphere anymore. You can't take CO2 and make rock with it anymore. So all the CO2 just accumulates in the atmosphere. All that stuff that's coming out of volcanoes accumulates in the atmosphere. This is a runaway greenhouse effect. There's no going back from it. Now the surface temperatures on Venus are way too hot to have a liquid ocean. So you're never going to have an ocean. You're never going to be able to pull CO2 out of the atmosphere, form more rocks, and start that cycle over again. It's a runaway effect. It's done. Done and dusted. Venus is a greenhouse planet. I mean, it's so cool. It's such a cool story, right? And such a cool comparison to Earth.
It is. But, and it also shows, again, what we've known for 200 years, that what carbon dioxide does. Carbon dioxide absorbs infrared radiation, which is heat. So, Jesse, what does this mean then? If we keep adding carbon dioxide to the atmosphere, as we are going to continue to do, what's the net effect? What happens?
Yeah, I mean, the net effect is we're going to be trapping more solar radiation, inside of the Earth. We're going to be trapping it inside of our atmosphere, and so then we get into the IPCC reports about what the impacts of climate change will be at a given CO2 concentration, and then we get into the climate change aspect of this.
So that's how you bridge the gap.
Exactly.
How does the greenhouse effect turn into a discussion regarding climate change? Well, more carbon dioxide means more trapped heat.
Right.
The science is there. It's solid. It's sound. I think that any discussion about this, it has to begin with what we know. Let's summarize it. What do we know?
Yeah. So we've gone from basically the understanding that the greenhouse effect has been known for a long time, back to the 1820s, right? Where people started to understand what the greenhouse effect was and that it was actively going on. And then we went into a little bit of an understanding of how the greenhouse effect actually works, right? In the distribution of radiation.
Yeah. You know how that radiation comes in as short wavelength and it gets absorbed and re-radiated as long wavelength. And that long wavelength cannot pass through the greenhouse gases that the short wavelength could. And so it's re-radiated back by those molecules again. And so you know what the net effect is? It lets heat in and it doesn't let it out.
That's right. And so then when we talked about CO2 being a major dominant greenhouse gas, how we produce CO2 as humans. And then we also got into the long carbon cycle, the short carbon cycle, and how really rocks actually control the distribution of CO2 and really moderate it and then we compared to our planetary twin, which is Venus.
Yeah, right. But rocks do control it, but now we have upset the balance as humans. And that's not open for debate, Jesse. When I first started teaching 24 years ago, there were 350 parts per million carbon dioxide molecules in the atmosphere. And today there's almost a 20% increase in a 20 plus year time span. That's a lot of carbon dioxide increase.
Yeah, so it's an interesting. I mean, that's interesting you bring this up because it's kind of difficult for people to understand what is a part per million, right? This is a difficult unit of measure to kind of understand, right? We understand percent, right? 1%, that's 1 in 100. But a part per million is hard to grasp, right?
It is. Yeah. If you had $1 million bills laying in front of you.
You got $1 million right now laying in front of you at your desk right now?
I do not.
Oh, bummer. I don't either.
If I did, and I can imagine that I did, if I had $1 million bills in front of me, and you took one of those bills away, that is 1 part per million.
Yeah, it's really, this is a difficult thing to comprehend, but that really puts it into context for me, right? CO2 concentrations that we're talking about are extremely small, but they're extremely important and extremely impactful. And that's because CO2 is a pretty powerful greenhouse gas. It speaks to the power of the greenhouse effect and how much it matters.
Yeah, it does. All right, well, hey, let's wrap this up, Jesse. So we've had a great time. I always do with you talking about stuff, but this is something that's important to me, and it's something that I really hope that we distilled it down so that we can talk about what we know and not what we think. Because the greenhouse effect is a fact, and then but then how do you bridge the gap between the greenhouse effect and actual climate change is not a far jump at all, and that's what I hope that we did today and accomplished today. So we thank you all for tuning in, and I just want to emphasize again that we absolutely love feedback.
Yeah, totally.
And so if you can hit us up.
Yeah, hit us up. Hit us up at all the social medias. We are at Planet Geocast. If you like what you're listening to here, give us a like and a subscribe, and leave us a review on your podcast server. And also remember, we're going to be doing the Geo Shorts, answering your questions. So send those our way as well. Yeah. Take care.